I request all the participants to mute your audio for the time being. If you have anything to say during the session, you can unmute yourself and then talk. This is to avoid the noise during the session. So hello and welcome everyone to the interactive live session of the course Microwave Engineering. I am Susan. I am a PhD scholar at Electrical Engineering Department, IIT Madras. I will be conducting a weekly 1-hour session on Google Meet every Friday from 7 p.m. to 8 p.m. So the aim of this session is to interact with you every week, solving some sample problems and clarifying your doubts. So every session will start with a brief summary of the video lectures and the syllabus covered in a particular week, followed by a tutorial session. So hope I will be able to keep you motivated throughout the journey of this course and help you attempt the weekly assignments with more confidence. So let me talk about the course a little bit. So the course on microwave engineering is intended to provide a foundation especially for the undergraduate students, but not limited to them. This will provide an overview of applications of microwave in communication and other areas. Design of different passive and active microwave circuits and subsystems are also covered in this particular course. So the prerequisites to the course is electromagnetic field theory, and so let me just start with some interactive polls. So you will be able to access the poll from your Google Meet. So I am just launching a poll. You can I hope you are able to see the poll right now. You can give your votes. So my first poll question is, it's a general question just to understand the learners. So as NPTEL learner, which of these category do you belong to? Are you a BTech student or an MTech student or a PhD scholar, or are you a working professional as a faculty in engineering college, or are you a working professional in industry? So I would like to know what as a learner which category you belong to. So I hope you can access the poll from the Google Meet. Down you can have the activities, where you have the activities. So from activities you can click on to the polls. So the poll will be visible to you and you can vote for the poll question. I hope all of you are able to access the poll. If anybody is facing a difficulty, please let me know. It's very easy to access. Down towards the right corner, you have activities. Once you select the activities, you get the polls, and then you can access the poll question. So I see that some of the learners are PhD scholars. Some might be working professionals. Yeah. So thank you for accessing the poll and voting for that. So let me go to another poll question. That's very interesting. A general question. Let me launch that. What is the frequency range used by telecom operators in India for 4G LTE band? 4G LTE band. So, any idea of what is the frequency range used by the telecom operators? So 4G network is something which is currently widely used by many, used by most of us. So, any guesses on what is the frequency range used by the telecom operators for 4G? You can access the poll down right corner of the Google Meet. You will get activities and you can access the poll. So if you are unable to access the poll, you can even type in the chat box if you have any idea of what is the frequency range used by the telecom operators. So there are options are 1.5 to 1.8 gigahertz. The second option is 2.3 to 2.4 gigahertz, and the third option is 4.2 to 4.4 gigahertz. So out of these three options, for 4G LTE band, we use 2.3 to 2.4 gigahertz. So this is very interesting because as we move on in the lectures, you have already seen the range of frequencies as in microwaves, that is ranging from the 300 megahertz to 300 gigahertz is called as microwaves. So when I say with respect to the wavelength, it varies from 1 millimeter to around 1 meter. So this microwaves frequency range, so especially this 4G band lies in the S band of microwaves. So as we have seen in the week 1 content, let me look at the week 1 content. So this is the week 1 lecture start with the introduction to microwave engineering, especially the frequency range, the history of microwaves, and took out some applications of microwaves. So I hope you might have come across applications of microwave. Can you please type in the chat box what are the application, what is the very first applications of microwaves? Any guesses? What is the very first application of microwave technology, or where it was used? You can always type in the chat box what do you think, or you can say any applications of microwaves in general. Yeah, I get responses, that is yeah, radar, yes. So that answers my question, that is the very first application of microwave was in World War, and they used initially for radars, for basically for the civilian and basically for the military surveillance and navigation. So nowadays radars have even civilian applications as well, for air traffic control, and even in cars we have small monitoring units where which is basic principle is based on the radars. So and communication, if you look at the communication aspect, we have somebody who says communication. So terrestrial and satellite communication is based on microwave technology. And to be specific about the medical applications, you might have come across biomedical area where sensing is one of the very widely used area for microwaves. And also if you are familiar with implantable antennas or implantable devices which works on microwave frequencies, that's also a very important application of this technology. And other than that, we have even industrial and commercial applications as well. So let me move on to the content, what we have covered in week 1. So first is microwave transmission lines and lumped circuit model. So could you tell any of the microwave transmission lines which you have come across in the literature? Any one of the transmission line? Could you name them? And please write in the chat box. I can I can see the chat box right now. Any of the microwave transmission lines which you have come across during the lectures? Yeah, right. As rightly said, coaxial cable. So that's one of the microwave transmission line where we have a inner conductor and the outer conductor separated by a dielectric. Yes, as another person pointed out, yes, microstrip line. That is where most of the current technology lies, wherein microstrip lines are being extensively used. Yes, let us move on. And we have learned about the lumped circuit model in the lectures. So as you can see in this figure here, so you have this microwave transmission line here. So this is the source. So this is the source and this is the load, and this is an input impedance of the source, and you see this is being denoted as the transmission line. So this transmission line has been represented using a lumped circuit model. So I hope you understand the significance of why we go for a lumped circuit model. So the small section of the transmission line is being used, is being so this is the small section of transmission line which is being represented by this particular model. So you can see this model has a resistance, an inductance, then then a conductance, and then a capacitance. So these are the primary constants of the transmission line as we have seen in the lectures. Now let us move on to okay, let us move on to the contents followed by that. So then we had a transmission line theory where the professor has discussed about telegrapher's equations and also on wave propagation on transmission line, then followed by the lossless transmission line without termination and with termination. So we will be having some sample problems in this particular area where we deal with a lossless line with termination. So followed by we discuss in the lecture 3 basically on lossy transmission line. So what are the lossy coefficients, loss coefficients, we discuss on that, and also the distortionless line. That is something which has been discussed in lecture 3. And the final lecture, I mean lecture 4 of week 1 was on Smith chart. That is a very important, yeah, that's a very important tool for the transmission line analysis problems. So this is a Smith chart having so the Smith chart, as you see here, I hope you remember. So these are the R circles of the Smith chart, and these are the X circles of the Smith chart. So these have been discussed in the class. So we will have some numericals based on that as well. So let us move on to learn to solve sample problems. So let me go to the very first question. In a lossless line, the phase velocity is 2.8 into 10 power 9 meter per second. If the characteristic impedance of the line is 50 ohms, capacitance per unit length of the line is. So as seen in the question, you can see it's a lossless transmission line, and the phase velocity, which is denoted by Vp, that is 2.8 into 10 power 9 meter per second, and the characteristic impedance Z0 is 50 ohms. So how do we get the capacitance? So as we have seen in the lumped circuit model, so any transmission line can be represented as RL, G and C. RL, G and C. So you are given with the transmission line characteristic impedance and also the phase velocity. That means the way on the medium, on the transmission line. But you are asked for this particular primary constant, that is C. So how do we calculate it? So the first understanding is this is a lossless transmission line. So what is the condition of a lossless transmission line? Can any one of you please type in the chat what is the condition for a lossless transmission line? It's a very simple condition. You can try to write in the chat box. What is the condition of a lossless transmission line? Yes, as Priyanka said, R is equal to G is equal to 0. Yes, and you have Z0, that is Z0, fundamental equation for Z0 is R plus J omega L divided by G plus J omega C. So when R and G both are 0 for a lossless transmission line, so your equation becomes Z0 is equal to root of L by C. And also the phase velocity, the fundamental equation of phase velocity is omega by beta, and here in case of a lossless transmission line, beta is omega root LC. This had been derived in the video lectures. I hope you remember. So then we get Vp as 1 by root LC. Now you have Z0 and Vp. Will you be able to calculate C from this? So the easy way to go ahead is take Z0 into Vp. So you get it as 1 by C. Z0 into Vp. Root of L by C into 1 by root LC. So Z0 into Vp is nothing but 50 into 2.8 into 10 power 9. And C can be calculated as 1 by 50 into 2.8 into 10 power 9. The final answer is 7.14 picofarad per meter. So you can calculate this and get this answer. So as you see, the answer is option C. So the question is capacitance in picofarad per meter. So something to note here. So here capacitance unit is picofarad per meter. That means it's a per unit length capacitance. Per unit length capacitance. And this is because basically the capacitance is distributed in the transmission line, and we are looking at a infinitesimal section of the transmission line which has this particular capacitance. So if you have the total length of the transmission line to be 10 meters or so, then this capacitance has to be, so 7.14 picofarad has to be multiplied by the 10 to get the total capacitance of the transmission line. So this is the basic idea. I hope you understand this. So any doubts in this question, you can please type in the chat or you can unmute yourself and ask. Or I will move on to the next question. If there are no doubts, I will move on to the next question. So as I see, there are no questions in the chat. So I hope I can move ahead. That is going to the second problem. So if you look at the problem 2, the lossless line, again the case is with the lossless line, and the characteristic impedance Z0 is 50 ohm and you have a load resistance. So this is a transmission line which is terminated with an impedance of 75. So to be specific, a resistance of 75 ohms. So I can write it as ZL is equal to 75 ohms. The frequency of operation is 1 gigahertz. So let me write it down. Frequency of operation is given to us and phase velocity is also given. Vp is 2.4 into 10 power 8 meter per second. Now the question is the location of the first voltage minimum from the load is. So now we need to think about a transmission line. Say you have a source, then you have so there is some impedance for the source, and then you have a transmission line. Yes, and then this transmission line is having an impedance of Z0 and this is being terminated with a load. Now when this is terminated with the load, there will be, so when if Z0 is not equal to ZL, then there will be reflections back. There will be reflections back. So we need to look at the reflection coefficient. So the point is, whenever there is a reflection, so there is a combination of incident wave and a reflected wave. So there are two traveling waves, one in plus Z direction and the other in the negative Z direction. So these two combine together to give a standing wave, and the standing wave has maximas and minimas. So as we see, we have already seen, you might have already seen in the lectures, say you have a standing wave something like this. You might have a standing wave like this, wherein this is the V max, or if I am plotting the voltage and if I am plotting the distance on the transmission line, so this is voltage maxima and this is a voltage minima. This need not be 0, this can be a value. So I am just representing it as V minima. So V max and V minima. So these two are separated by a distance lambda by 4. So adjacent maxima and minima are separated by a distance of lambda by 4. So because here we have the load impedance or the load resistance ZL, load resistance ZL is greater than Z0, and also we know that this is a real impedance. In fact, I can represent it as RL, which is a real impedance, which is not does not have a reactive component. So then this is the V max, this point is the V max, and this V max is at the load. So this is, so if I say this is the distance from the load and this is the place where the load is there. This is the place where the load is there, and this is the distance from the load. Distance from the load. So this is V max and this is V minimum, and the distance between these two is lambda by 4. So here we have F and Vp, and the question here is location of first voltage minimum from the load is. So it is very clear, location of the first minimum is lambda by 4 from the load. So how do we calculate that? So the L is equal to lambda by 4. So we need to understand how to calculate lambda. So this is 2 pi by beta, where beta can be written as 2 pi by so we can write beta in terms of omega by Vp, and this comes out to be 2 pi by omega can be written as 2 pi f, and Vp, so cancelling these two, Vp by f, so Vp is 2.4 into 10 power 8 divided by frequency is 1 gigahertz, giga is 10 power 9. So the answer is 0.24 meters, 0.24 meters, or I can say in centimeters 24 centimeters. So this is lambda, this is the wavelength. Now the distance from the load to the first minima, that distance L is equal to lambda by 4. So 24 by 4 gives me 6 centimeters. So here the answer is option B. This is the length at which, or the distance at which there is, okay. Subhashish Barik, can you unmute yourself and ask your question?
Yeah, thank you. So the answer is 6 centimeter. So I was wondering if the information about Z0 and ZL are just redundant here. I mean, we do not have to use, that's just there.
Okay. So to answer your question, so I hope everybody understood his question. So he is asking whether Z0 and ZL matter here. So as I said in the beginning, whenever ZL is not equal to Z0, we have a reflection coefficient, then there is a standing wave. That is first one point. Second point is, if we have a real impedance or if you have a reactive impedance. So when you have a real impedance, the maximum, the voltage maximum is at the load. When you have a reactive impedance, that's not the case, because you know reactive impedance will have some phase shift, which that will give a phase shift, due to which Vmax won't be at the load end, exactly at the load end. So the information on load resistance and also characteristic impedance is very important here. So Subhashish, I hope I have answered your question.
Yes, but slightly, I mean, the position of Vmax, no matter where Vmax is, the distance between Vmax and Vmin would be lambda by 4, right?
Yes, that's true.
All right, thank you.
Yeah. So the question is basically location of the first voltage minimum from the load. So that's why we need to understand whether we have a maxima at the load end, or we have a minima at the load end. That is very important to us.
All right, thank you.
Yeah. So I hope there are no other questions. We can move on. Okay. So let me go to the third question, that is, if the VSWR on a lossless transmission line terminated to a load is 4. So the information given in the question is about VSWR. So I hope you remember what is VSWR, that is voltage standing wave ratio, denoted by rho. Okay, let me come to the question once again. So the fraction of incident power transferred to the load. So we need to tell what fraction of incident power is being transferred to the load. So to get into this question, let's try to understand the question once again. So we have a transmission line here, and there is a load. So this load and this characteristic impedance is not matching. So then you have a reflection, then you have a standing wave, which is a combination of both the waves, both traveling waves traveling in opposite direction. And let me tell you, the power transfer okay, let me ask this question to you. What do you think, when will be the maximum power be transferred from the transmission line to this load? What do you think? Under
When they are
what?
the same.
Yeah, when they are same. So whenever Z0 is equal to ZL, we have the maximum power transferred. So whenever it is not equal, we have a fraction of power being transferred. So we are trying to understand what is that fraction. So let me write this for you. So from the VSWR, you can calculate the reflection coefficient using the formula rho minus 1 by rho plus 1. So so the value of gamma is 3 by 5. Now for given reflection coefficient, so that is a voltage reflection coefficient. Now we need to understand what is the power. So let me tell you, the power transferred, or how much power is being transferred, can be written as, so incident power into 1 minus mod gamma square. So I hope this had been clear from the lectures. So as I see here, so this is the voltage reflection coefficient. So to get the power, we have to take the square of this, and to get the transmitted power, then you have to take 1 minus mod gamma square. So the fraction which is being asked in this question will be Pt by P in, that is equal to 1 minus mod gamma square. So I can solve it as 1 minus 3 by 5 square, which is 1 minus 9 by 25, which is 16 by 25. So the answer option is C. So I hope this is clear to all of you. Any doubts, you can type in the chat or unmute yourself and ask, or I'll move on to the next question. Okay, so let me move to the fourth problem. So that's again that's on a distortionless line. Okay, let me read the question first. A distortionless line has an attenuation constant. So let me represent this attenuation constant for you. This is represented with the symbol alpha, 0.002 Napier per meter, and resistance per unit length. So this is a primary constant of the transmission line, which is denoted as R, and that is being written as 0.1 ohm per meter. So I hope by now you remember that this resistance is per unit length, which is the resistance of that infinitesimally small section of the transmission line. And you need to calculate the characteristic impedance, that means Z0 of this line, of this transmission line. So let me tell you, yeah, there is a question in the chat. Let me just see that. Beta is 0 for this. Okay, there is no mention of beta here. Doesn't mean that it is 0. So to answer that question, let me talk about or refresh your concept on distortionless transmission line a little bit. So I hope you remember where professor has discussed about the distortionless transmission line. So as you see, the propagation constant gamma is represented as alpha plus j beta, and this can be written as r plus j omega l, square root of r plus j omega l into g plus j omega c. So now you see that this is alpha, which is a real part of this, and this is beta. And once you apply the condition for distortionless transmission line, that is r by l is equal to g by c, you have seen in the lectures that alpha becomes r into root of c by l, and beta is omega root lc. So this is the condition for a this is the condition for a distortionless transmission line, and under this condition alpha and beta becomes this. So the important point to note here is this attenuation constant is independent of omega, and beta, the phase constant, is dependent on omega. So we are given with alpha here. So we know alpha here. So using this equation, I can write alpha and z naught is to be found. Okay, alpha is 0.002 is equal to, r is also given here. R is given as 0.1 into root of c by l. So all of you know that, okay, let me write it like that. So all of you know that in this transmission, distortionless line, under the condition of distortionless line, characteristic impedance becomes root of L by C. So I can write this as 0.1 divided by Z naught is equal to 0.002. From this, we can calculate the value of Z naught. Can anyone of you please type in the chat what is Z naught? Value of Z naught, it's very easy to calculate, nothing much. 0.1 by 0.002, yes, 50 ohms. So this is the characteristic impedance of the transmission line. Thank you for typing in. Yeah, so I hope the concept of distortionless line is clear to you. So this is a question based on the condition for distortionless line, and also what is the I hope you got the idea of attenuation constant in case of a distortionless line. So are there any question? Can we move ahead? Okay, so let us move on to the problem 5. So consider a load impedance ZL is equal to 50 plus J50 plotted on a Smith chart. So I hope you might have covered the Smith chart in the lectures, which was in lecture 4. Considering a normalizing impedance of 50 ohm, radius of resistance circle passing through the load impedance point on the Smith chart is. So let us look at the information given in the question. That is, the load impedance is 50 plus J50 and the characteristic impedance is 50 ohms. And so can you tell me what will be the normalized impedance? So we need normalized impedance to plot this on the Smith chart. Yeah. So as somebody rightly pointed out, it is calculated by ZL by Z naught. So 1 plus J, ZL by Z naught. So this can be plotted on the Smith chart. So as I have shown you the Smith chart before, so here you have the R circles. So here you have the R circles and then you have the X circles. So here the R value is 1 and X value is also 1. When we represent it as 1 plus J, when the impedance is 1 plus J, R is equal to 1 and also X is equal to 1. So we need to find an intersecting point of R is equal to 1 circle. So that is R is equal to 1 circle and X is equal to 1 circle. So this is the X is equal to 1 circle. So this will be the impedance point 1 plus J. 1 plus J. Okay. So let me move on to the question once again. Yeah. So the question is little tricky. The question is on radius of the resistance circle passing through the load impedance point on the Smith chart is. So to calculate the radius of the resistance circle, we need to use the equation of resistance circle here. Gamma R minus RL by 1 plus RL the whole square plus gamma I square is equal to 1 by 1 plus RL the whole square. So this is an equation of the circle. From this we know this RL by 1 plus RL. So here RL is the value of so when we write this load impedance, this is can be represented like RL plus JXL. So RL is 1. So 1 by 1 plus 1. So the radius is 1 by 2. So the answer option is option B. So this equation has been covered in the video lectures. If you need any further more clarifications, you can in fact look into how it is being derived. So this is the radius of the resistance circle passing through the load impedance point. So okay, I hope there are no questions. Okay, let me move on to the next question. So that's problem 6. Okay, so this is on a lossless transmission line of characteristic impedance 50 ohm is terminated to a load resistance of 100 ohm. The return loss in dB. So we need to understand the terminology return loss here. So what do you mean by return loss? So if you know that, it is very easy to solve this question. So again, this is a lossless transmission line. Z0 is 50 ohms and the load resistance ZL is 100 ohm. Now, whenever there is an impedance mismatch, that is the characteristic impedance is not matching to the load impedance, there will be a reflection, and you can calculate that reflection coefficient. Can you please calculate it and let me know? I hope all of you know the equation for calculating the reflection coefficient. We have already discussed it one or two times before. So the reflection coefficient, can you try to calculate it and let me know? So the equation is ZL minus Z0 by ZL plus Z0. Anybody please type in the chat what answer you get. Yeah. Yes, Thank you for typing in. So ZL is 100 minus 50 by 100 plus 50, which is nothing but 1 by 3 or 0.33, as many of you have written. Yes. So now once if you know the reflection coefficient, you need to tell what is return loss. So return loss or RL, that in dB. Okay, so to calculate that, we need to take minus 20 log of modulus of gamma. So minus 20 log of 1 by 3, and this, can you please find out the answers? Yeah, 9.54 dB. So the option will be option A. The answer option is option A. So that is the return loss in dB. So in this terminology, return loss is being used in many of the places, especially when we consider microwave antennas. We don't quite use reflection coefficient. Mostly we represent or take it as return loss for the antenna at particular reflection of at a particular wavelength. So let me move on to the seventh problem. Input impedance of a given length of lossless short-circuited transmission line of characteristic impedance 50 ohm is found to be J50 root 3 ohms. So length of the transmission line section is. So the given information is, you have a transmission line which is lossless and also short circuited. So I hope you have already got the concept of short circuited, what a short circuited transmission line is. So basically, if you have a transmission line for which the load impedance, the ZL, is 0, or the ZL is equal to 0, or we call it as a short circuited transmission line. For such a transmission line having a characteristic impedance of 50 ohm, the input impedance, that is Zin, is being given as J50 root 3. Now you are being asked about the length of this particular transmission line. So any guesses how do we proceed about this? So we need to basically understand when the load impedance is 0, or when the transmission line is short circuited, what is Zin, input impedance? We have looked at the transmission line impedance, and there were two special cases being discussed in the lectures. So for a short circuited transmission line, this input impedance becomes JZ0 tan beta L. So this is particularly for a lossless transmission line. That is why alpha becomes 0 here. We have only beta here. So now you know this value is J50 root 3, and equating that to J into Z0 is 50 into tan beta L. And you get tan beta L is equal to root 3. So beta L is equal to pi by 3. And can you please let me know what is length of that transmission line? You can write beta as 2 pi by lambda. So pi and pi gets cancelled, and the length of the transmission line is lambda by 6. Lambda by 6. So I hope this is clear. Any doubts here? Okay, if there are no doubts, we'll move on to the next question. So the next question is about for a transmission line, given that R, L, G, C and Z naught respectively represent the resistance per unit length, inductance per unit length, conductance per unit length and capacitance per unit length, and characteristic impedance in absence of any loss. So you have basically a lossless transmission line with parameters, the primary constants RLGC and also the characteristic impedance Z0. So if at the operating frequency omega, given that R is much less than omega L and also G is much less than omega C, which one of the following expressions represents attenuation constant alpha of the transmission line? So you are given with a condition for R and G. You need to find the expression for alpha in this case, in this question. So let us start from what we know about the propagation constant. So we all know that gamma is equal to root of r plus j omega L into g plus j omega C. So this is the fundamental formula of the propagation constant. So now let me try to expand that to make it more clear to you. So Rg plus uh, j omega L G plus j omega R C minus, so j omega into j omega becomes minus omega square L C. So now let's try to take out this particular term minus omega square L C outside. So then that becomes, so outside the square root, this becomes j omega square root of LC, and inside you have this particular term becomes, so divided by this entire term. So Rg divided by minus omega square LC plus j omega Lg divided by minus omega square LC plus j omega RC divided by minus omega square LC. Then, so now what we can do is, so if you try to simplify, this becomes little simple. Try to simplify. So let me write that simplified for you. J omega root LC into square root of, I think,
Shouldn't there be a minus one in the
one term. So it's not minus 1, it's plus 1 because we have taken out minus omega square LC
Ah, yes.
outside. Yeah. Okay. So thank you for reminding me. So the condition here, let us apply the condition here. R very less than omega L and G very less than omega C. So if you take R into G is very less than omega square LC. So if you look at this particular term, R into G very less than omega square LC. So this term can be neglected. So what remains here is 1 minus j into r by omega L plus g by omega c. Now this can be simplified as so let me try to make it little more simple. So we are looking at only alpha. So we need, so basically gamma is alpha plus j beta. So this is the real part. So when we simplify for this alpha, we are only looking at the real part of this. So make it more clear, j omega root LC into, so under square root of this term becomes, so I can write it like 1, say this is 1 plus x the whole raised to half. Using binomial expansion I can make it as 1 plus 1 by 2 x. So with this I can make it as 1 minus j by 2 into r by omega L plus g by omega c. So now if you cross multiply, the first term will be imaginary term and the second term will be a real term. So the second term is where the attenuation constant is. So let us expand the second term alone. So the second term alone becomes j into j becomes minus 1 plus, so that becomes omega root LC. So basically the final answer is alpha is equal to 1 by 2 into r into root of c by L plus second term will be g into root of L by c. So we are looking at only the real part of the gamma, real part of gamma. So that will give you the attenuation constant alpha. So here to get the answer in the form of our answer options, we need to make a little more changes here. So we already know that root of L by C is Z0. So basically I can write this as 1 by 2 R by Z0 plus G into Z0. So as we see, this option B is the right answer.
Uh, just a quick comment. I
Yeah,
think we can just use the dimensional analysis here to eliminate two of the answers because I
yeah,
mean
yeah.
it has to be r by z naught. It can never be r into z naught, right? So that's a maybe.
Yeah, okay. Yeah, thank you for pointing out Subhashish. Yeah, basically to answer most of the MCQs, you can always have such kind of analysis that helps you to find the answers quickly. So basically what I have discussed is a conventional way in which you can approach or arrive at the answer. Always you can use the tricky way out there. Yeah, thanks for pointing out. So thank you all. This is so today's session. I had I tried to cover the first week's content, the sample problems based on that. So if you have any questions, any you can ask, or we will try to close the session today. Always you can ask any doubts in the discussion forum. Our team will be looking at that and trying to answer it as early as possible. And I hope the cooperation will be there for the even for the next session we will have for the week 2. We'll try to help you out with sample problems in the week 2 next Friday from 7 p.m. to 8 p.m. Thank you.